So, we have an assignment due on Thursday. Lots of work to do.
Is the assignment going to be due at the regular time, 5:30?
Yeah.
Okay.
Regular time. So we'll have some extra office hours to try to answer questions you might have at this point. Toby has his office hours today, and I'll have some extra office hours on Wednesday. All right. And that evening we have our makeup lecture we missed last Thursday. And of course we have an exam coming. So we'll have on Friday a review session during our problem session time. And we'll discuss things more. The exam covers everything up to lecture 8, which means it doesn't include what we're doing right now on fine structure and hyperfine structure and the last this assignment and the second problem on problem set 5. Okay, so it's not going to cover that material. So what that means is that it covers what we discussed relative to the interaction of charges with electromagnetic fields, gauge potentials, Berry's phase, stuff like that, geometric phases, the hydrogen atom, and the sort of basic perturbation theory. All right? Yeah.
What resources can we bring, if any?
I will discuss that. It's going to be closed book up to a set of, sort of 1 page, 2 sides kind of thing. All right. So, in the last couple of lectures, we've been discussing what I would call the real hydrogen atom. Okay? So, what we've been discussing is the description of the energy levels of the hydrogen atom, including some important corrections to the most basic Coulomb interaction between the electron and the proton. Okay? So, what that means is that we have our 0th order Hamiltonian, which is the binding interaction between the electron and the proton. And that gives us the basic spectrum, though the energy scale associated with H0 is the Hartree. Okay? So that gives us the scale associated with the energy separation between the ground state and the first excited state. Then we have corrections to that. We have the fine structure that corrections arising from relativistic effects, and that included the spin-orbit interaction and some corrections from the relativistic kinetic energy and the relativistic Ziegler-Wegen of the relativistic electron. And those corrections were down from the Hartree by powers of the fine structure constant squared. Okay, so it's a small energy relative to the 0th order energy, so it's a perturbation to that. And then we saw last lecture the hyperfine interaction. The hyperfine interaction arises from the nuclear spin. So when we introduced the fine structure, the electron spin played an important role in the first relativistic corrections because of the spin-orbit coupling. but the effect of the nuclear spin comes in as well. And there is a effective magnetic dipole-dipole interaction between the magnetic dipole associated with the internal spin of the proton and the magnetic dipole moment associated with the internal spin of the electron. And those energies are smaller than the energy scales associated with the fine structure by the ratio of the electron mass to the proton mass. So that's down by, another factor of 10 to the minus 3, 10 to the minus 4, okay? So this can be considered a perturbation to this Hamiltonian, all right? And so when we put all that together, what we saw was that if we thought about the energy spectrum of hydrogen, let's just look at the first and second excited state. Okay? So in zeroth order, we had the usual orbitals of hydrogen, right? And we specified those energy levels by the quantum numbers, the principal quantum number, the orbital angular momentum magnitude quantum number L, and the projectional orbital angular momentum m sub L. Okay, those are the three quantum numbers, and we had this kind of energy spectrum. And because of hydrogen has this 1 over r potential, we have this accidental degeneracy, although it's really not an accident, it's a higher order symmetry between different L's. Okay, that's not true for any other atom with more than one electron. When we added in the fine structure, firstly, what happens is that we split out states now that were previously degenerate. Okay? And that's a general property of degenerate perturbation theory. When you have degeneracies, often they're due to symmetries. And when you add the perturbation, if the perturbation doesn't respect that symmetry, then the new eigenstates won't be degenerate completely. Okay? So there was this SO4 symmetry that was buried in here, which is why the L's were degenerate. And then when we added in the spin-orbit coupling, we broke that SO4 degeneracy, and we ended up with the splitting. We have this additional extra splitting between the different J's because of the quantized field. It's a complicated detail, but it's there. But one of the points I want to emphasize here is now, when we added in the fine structure and the spin-orbit interaction, then the good quantum numbers have changed. So now, instead, really buried in here was S and M sub S. We ignored it because it played no role in the zeroth order. But when we added in the spin-orbit coupling, these are not the good quantum numbers anymore. Now the good quantum numbers are J and M sub J instead of M sub L and M sub S. They're no longer good quantum numbers, meaning that they don't respect the symmetry of the Hamiltonian anymore. And so we have new notation here. We specify our electron orbital, including the effective electron spin, no longer just as the principal. We had the 1s state and the 2s state and the 2p state. We have this little subscript here which tells us which J it is. Okay? That's the jargon, that's the notation. So we have the 1s 1/2 orbital, we have, well, this should be the 2s 1/2 orbital, the 2p 1/2 orbital. They're really not orbitals, they involve the coupling of the orbital and the spin, right? And each one of these states is now degenerate with with the projection of m sub j, so there's 2j plus 1 different sublevels within this for the given value of j, right? And this splitting, the fine structure splitting here, I mean, this was huge. This is like 10, you know, this is like a hard UV photon, and this is a microwave type splitting in the fine structure. It's a tiny fraction of the splitting. That's why it's fine structure. Okay? Then when we added in the nuclear spin, now, well, we forgot about that there's an I m sub I being the magnitude of the nuclear spin. In this case, for hydrogen, that's a half for a proton. And now these guys get coupled to F. So F is the total angular momentum of the atom involving both the total electron angular momentum and the nuclear spin angular momentum, and we call that F. So now F is the good quantum number once we include the hyperfine coupling. And this splits up this state into a state with total F. Since J was a half and I is a half, I can have F equals 0 or F equals 1. This guy, what are the possible values of F? Well, J is a half. Again, I have an F equals 0 and F equals 1. Hyperfine splitting in the excited state. Again, for the P 1/2, the 2s 1/2 also gets split into an F equals 1 and an F equals 0. And what about the 2p 3/2? What possible values of F can I have there?
3, 2, 1, 0.
Well, I'm adding J is 3/2 to I is a half, right? I is the spin of the nucleus. So it could be 2 or 1, right? Because I can add the total angular momentum, F, goes between I plus S and the magnitude of I minus S, right? No, in this case it's J. And J is 3/2 and I is a half, right? So the possible values here are F is 2 and F is 1. And this splitting is on the order of a few megahertz, I believe. I mean, remind myself, I don't remember what it is in hydrogen. So this splitting, just to get a sense of scale here, is 23.7 megahertz. And this is 177 megahertz. And this is 58.2 megahertz. Okay? So it's hyperfine. It's a much smaller splitting than the fine structure by a factor of 1,000, as kind of expected from the ratio of the electron mass to the proton mass. Okay? Now, is that the whole story? Sort of, but not quite. Each one of these levels is possibly degenerate. What is the degeneracy of this level, F equals 0? It doesn't happen. There's only one state, the state with m sub F equals 0. But what about this state?
3.
It has 3, right? Because there are always 2F plus 1 different projections. In this case, they all have the same energy. So this is triply degenerate.
Do we reduce the whole?
Well, maybe some of that. And so forth and so on. Now, of course, why is there that degeneracy? Is that an accidental degeneracy? Or is it an essential degeneracy having to do with symmetry?
Essential?
It's essential. And what symmetry is it associated with?
Use rotation.
Rotation. It's totally, there is no direction in space that's deciding what is the z-axis. It's rotationally symmetric. So all different projections of angular momentum have the same energy, because how would the hydrogen atom know what direction we're calling z? That's our choice. Okay? So the degeneracy here is associated with the essential symmetry associated with the isotropy of the universe, so to speak. Now, of course, we could break that degeneracy. We can add, for example, if I break the degeneracy, by an addition of an external B field. So now I put on a magnetic field in some space, some direction, and there is a direction space that's different from all the others. And so there is a new perturbation, H, which I'll call the Zeeman interaction, which is the interaction of the atomic magnetic dipole moment with the external magnetic field. Okay? And as Stephen mentioned, this is a problem you're studying in your homework right now. You've done it. And what this will do, generally, is cause us to break the degeneracy between the different m sub f's within a given subspace with a given f. Okay? Now, whether I treat this as a perturbation relative to the hyperfine structure, or whether I treat the hyperfine structure as a perturbation relative to this, depends on how big the magnetic field is. And that's one of the things you're looking at in your homework. Effectively, when the Bohr magneton times the magnetic field is much, much less than the hyperfine splitting of energy, well, then this is a perturbation relative to this. In which case, we would do degenerate perturbation theory within each subspace individually, right? So what will happen in that case, for example, let's zoom in on the, so here's my 1s, 1/2 electronic ground state. I call it the electronic ground state because it's not really, the absolute ground state is this, but these are all associated with this 1s, 1/2 electronic orbital, right? And this is my f equals 1, and this is my f equals 0. Okay? Now, if I put on a weak magnetic field, if this is small compared to this, well, then this is a perturbation with respect to this, and that means that these remain good quantum numbers. So with the magnetic field on, depending on the direction, what will happen is I'll split this energy, this state, this guy goes. As to say, in this limit, what you will show is that the Zeeman interaction is proportional to B dot F. In other words, we can look at this, if I call this the z direction, which is the natural thing to do, that defines what we call the quantization axis. Okay, that's our choice. Then the eigenvalues of this is not a vector, this is an operator. This Zeeman interaction is diagonalized in the m sub f basis. And so I just get a shift proportional to m sub f. The m sub f equals 0 don't shift. And the m sub f equals 1 goes one way, the m sub f equals minus 1 goes the other way, depending on the direction of the B field. Okay? And the splitting then is known as the Zeeman splitting. So the Zeeman interaction is the interaction of the atom with the electric field. The Stark was with the the Zeeman was the magnetic field, the Stark with the electric field. That's just jargon.
So when you do the Zeeman, it ends up with two terms, one dependent on S or J, and one dependent on I.
You do, but in the limit that this is true, then for all we can rewrite that as an effective interaction that's just proportional to F. Because we can do degenerate perturbation theory restricted to that subspace. We don't have to think about this state at all. Because that, when the Zeeman splitting is tiny compared to the hyperfine splitting, then it's all restricted to that degenerate subspace. That's what degenerate perturbation theory is all about. On the other hand, as if we go into the opposite regime, as if the magnetic field is huge, you put on a superconducting magnet with many Tesla of magnetic fields on it, well then the interaction between the electron and the nuclear spin is a tiny interaction compared to the interaction of the electron with the superconducting magnet. In which case, this would look quite different. And that's your homework, to think about that. Okay? But the key point is there, once we put on the magnetic field, then we split out all the states. And we have all possible states. Remember, the total Hilbert space within a given subspace depends on L, S, and I. So what's the dimension of the subspace associated with a particular principal quantum number n? Well, for L, I have 2L plus 1. So the total dimension of each of these Hilbert spaces here is 2L plus 1 times 2S plus 1 times 2I plus 1. Right? And in this case, this is 2, this is 2, so it's 4 times this. Right? So when L is 0, there are 4 sublevels. That's good. Here they are. When L is 1, well then I'm going to have 3 times as more sublevels. Okay? Then for L equals 0, and they'll all split out. You'll uncouple the nuclear spin from the electron spin. Of course, if we cranked it up even higher, then ultimately I can mix together, I can uncouple the electron spin from the orbital, right? I can decouple the spin-orbit interaction if I had a massive magnetic field. And people have done such experiments as well. All right? So one last thing. The reason the quantum number is called M is that these levels are sometimes known as the magnetic sublevels, or the Zeeman sublevels. Both terms are used interchangeably. That's why they're called M. All right. Very good. Yeah.
Is there a state in which all these perturbations make it so that every single state has degeneracy just 1?
Absolutely. So, as I was saying, when you put on a magnetic field that's strong enough, that this dominates over all the couplings between the different spins, then they're all very separate energies. So it will depend independently on m sub L, m sub I, and m sub S, right? Whereas what we did is first we coupled L and S together to get m sub J, and then we coupled m sub J with m sub I to get m sub F. And by putting on a big enough magnetic field, I can decouple all of those guys. But that would take a massive magnetic field. All right, very good. Okay, so I'm going to switch gears a little bit right now. What we've been talking about over the last number of weeks is time-independent perturbation theory. And so that's a situation in which we imagine that there is the Hamiltonian could be broken down into some Hamiltonian that had some dominant energy scale associated with it, and a small force or small energy scale Hamiltonian H1. And this was what we've just been studying. This is important when we're thinking about corrections, particularly to the energy structure of matter, atoms, molecules, condensed matter, what have you. Okay? And so, loosely speaking, as sort of a paradigm that we've thought about, okay, if we thought about, for example, a spin in a magnetic field as one kind of example of that, where we have some big magnetic field V0, and we put on some tiny magnetic field V1 relative to it. And we ask, we have this kind of Hamiltonian where we write H like this. There's the dominant energy scale and then perturbations associated with this, right? And, to lowest order, all this does is there is a slight shift in the energy levels associated with this small magnetic field and, a small change in what the new energy eigenvectors are. For example, in the absence of V1, they would be spin up and spin down along V1, and now they're spin up and spin down along, this direction. Those are my new energy eigenstates of the system. Now, what we're interested in is what happens when I introduce a perturbation that is time dependent, but it's still thought to be small compared to this. Well, there's something very important that happens when we know that that's true, and we're familiar with that in the context of classical physics as well. If I have some system that has some strong, say, binding that's described by some Hamiltonian, and then I apply a perturbing force to it, and that perturbing force is time dependent, even if that force is tiny, absolutely tiny in amplitude, if the time dependence is just right, it can have a huge effect on the evolution of the system. So the most important thing about time-dependent perturbation theory is the phenomenon of resonance. Resonance happens when, even though the amplitude or the force that's being applied is absolutely tiny compared to the internal forces of the system, it can have a profound effect on the evolution of the system, right? So classically, I have, my mass on a spring with some, and this could be a huge restoring force, right? And now I apply this tiny force to it as a function of time, where this applied force is absolutely tiny compared to that, but nonetheless can cause this thing to move by huge amounts. And the reason is because if the timing of that force is just right, it adds in phase in just the right way that it builds up and makes a resonance. Okay? Or in the frequency domain, if the frequency content, if I did a Fourier transform of this applied force, and if there was a strong component at a frequency component that matched the resonance frequency, well then there'll be a huge force associated with that. And the same thing is true in thinking about this kind of problem. So let's just imagine for a moment classically, and we're going to study this in details. Let's suppose I have a strong magnetic field, V naught, and I have some magnetic moment, mu, that is processing around this guy at frequency omega naught, the gyromagnetic ratio times B naught, right? So if we have a spin, mu, it'll process around the magnetic field. Now, if I apply some other magnetic field that's tiny against it, well, it's just going to tilt this slightly. It's going to still process around this direction, but it's going to process around that direction with effectively just a slight change in the frequency, right? That's like my time-independent perturbation here. But suppose I take this applied magnetic field, V1, and I rotate it around. So I take this tiny magnetic field and I rotate it around at frequency omega naught. What's going to happen? Well, if I go into the rotating frame, co-rotating with my magnetic field, in the frame of this, it looks like a static magnetic field, right? And if I have a static magnetic field, and I have a spin that's perpendicular, or nearly perpendicular to that, what's it going to do? So let's imagine this system. Here's my V1, small in amplitude. Here's my spin in the rotating frame. What's it going to do? It's going to process around this. It's going to feel a torque. around that. And it's going to precess like this, with a frequency that's much smaller than omega naught, but it will precess. And it's going to go all the way from basically down to up. Even though this is a tiny amplitude, if the frequency of rotation matches this frequency of precession, that torque will add up in the same way that the force, if the force that I knock this with is exactly the right frequency, it's going to add up and cause resonance, right? So this guy is trying to, will torque around the combination of this, and if they move together in just the right way, it'll, and this whole thing is spinning around at frequency this. It's hard to wrap your brain around that. So this guy is going from down to up, but at the same time going around like that. The point is that if I have a time-dependent applied force, and if the time dependent of that force is on resonance, well, then it adds up a lot. Okay? Now, we know that this picture basically describes, and we're going to solve this problem in a couple of lectures. This is quantum mechanics too, right? I mean, because the spin processing around is the solution of its spin 1/2 particle. So you should keep that in mind. But that's why we care about time-dependent perturbation theory. It's because it's not so much about, I mean, it's true that there will also be slight changes to the energy levels, and of course, what the energy levels are, we have the instantaneous eigenstates and all that, because it's a time-dependent system. We're less interested in time-dependent perturbation of what the shift of the stationary states is than what is the time evolution of the system under the application of a time-dependent Hamiltonian. Now, some of that we've solved already. I mean, we've solved some problems of time-dependent Hamiltonians. We looked at, for example, adiabatic following, right? I mean, if I look at this problem, let's go back to this again, we solved this problem where we saw, oh, look, if I take this and I have some magnetic field and I change it as a function of time, I can get the spin to adiabatically follow, for example. That's an example of a time-dependent perturbation that we've already solved. But we want to look at this now in a little bit more general context, and in particular in situations where the applied Hamiltonian can be considered as a perturbation compared to the zeroth order. Okay? So that's our research program for the next few lectures. All right? So, how are we going to, so if we want to do that, we're going to build a little bit of formalism to deal with this. So let's begin. So the generic situation is usually written this way. But typically, instead of calling it H1, we would say, okay, I have my total Hamiltonian, which is a function of time, and we have the zeroth order Hamiltonian, and then we'll call this other thing the interaction Hamiltonian. That's usually the language we use when we're talking about this. So for example, this might be the hydrogen atom is H0, and H int might be a time-dependent magnetic field. Or it might be we apply a laser which has an oscillating electric and magnetic fields that are then interacting with the atom. Okay? That's the kind of situation we would typically deal with. And what we want to solve is the time-dependent Schrodinger equation, not the time independence. We want to solve for things like resonance. So we want to seek to solve okay? This is in the Schrodinger picture. Of course, it's equivalent to saying right, where the time evolution operator U is generated infinitesimally by the Hamiltonian. Now, we've kind of been doing that from early days of this course last semester. But when we typically solve this problem, our Hamiltonian was not time dependent. When we had a time independent Hamiltonian, then, you know, we have the solution. It's trivial to write down at least as an equation. That's what it is, right? But when H is time dependent, all bets are off, okay? If H were a number, if these were not operators, if these were functions that were C numbers that commuted and we didn't have to worry about the matrix nature of these, or the operator nature of these operators, then we would naively write well, we just integrate, right? We write this as this, and then we have the log, and then we have the integral, and this would be e to the minus I over h bar, the integral of 0 to t dt prime h of t prime. That's what we might have thought if we just didn't worry about anything and just treated these like functions. That's the integral of that problem. But this is, as we will see, only true if the Hamiltonian operator commutes with itself at all times. So that's not generally the solution, which is what makes this problem hard. All right? So, how do we do it? Well, in the same way that we had, we're considering in time independent perturbation theory, typically the way this works is that we know the solution to the time independent Hamiltonian eigenstates. We know the spectrum of this. This might be the hydrogen atom, okay? And in that case, if this were just we would know what the time evolution operator is associated with H0. It would just be the exponentiation of this with H0, and we would know that. So that's a kind of known time evolution that we can kind of already take out of the problem because we know it. Okay? So the way we do that is to try to put this, take this time evolution out of the problem. Take it, instead of having our state evolve according to the full Hamiltonian. We want to just have it evolve according to the part we don't know. So the way we do that is similar to what we did when we went from the Schrödinger picture to the Heisenberg picture. In the Heisenberg picture, we took the time evolution out of the states completely, altogether, and put it all together in the operators. Now we want to kind of go partially there. We're going to take part of the time evolution out of the states, the part that has to do with the free evolution, the evolution in the absence of the interaction, out of the states, and put that in the operators, and still leave this part in the states. So let me remind you about the Schrödinger picture, the Heisenberg picture, and now what we're going to talk about, the interaction picture. Okay? It's kind of an intermediate. So recall, in the Schrödinger picture, which is what I've written here, so let me just emphasize that by putting, this is the Schrödinger state in the Schrödinger picture. So in the Schrödinger picture, the Schrödinger observables are time independent. And the states are time dependent. I guess I'll put that outside the cat. Or equivalently, the states evolve according to a differential equation, where this is the total Hamiltonian. Right? And we have the total time evolution operator. Which satisfies this differential equation, where this is the total Hamiltonian. Okay, so that's the Schrödinger picture. Then we had the Heisenberg picture. Good old Heisenberg. Say his name. All right. And in the Heisenberg picture, we have the other thing. We found in the Heisenberg picture, the state is time independent. And the observable evolves in time as a unitary transformation relative to the total time evolution. Or equivalently, the operators evolve according to a differential equation, which we call the Heisenberg equation of motion. All right? Either way, we get the same thing. And of course, these two pictures agree under the initial condition that the time evolution, that at time t equals 0, the Heisenberg operator is given by the Schrödinger operator, and the Schrödinger state at time t equals 0 is the Heisenberg state. So then the two pictures agree by just setting those initial conditions. Okay? Now we're going to define a new the interaction picture. Okay, and it's kind of intermediate between the Heisenberg picture and the Schrodinger picture. Instead of having in the Heisenberg picture, the operators evolved according to the full time evolution operator. In the interaction picture, we're gonna take out the free evolution. So let me just write this way. Take free H0 evolution out of the states and put it in the operators. Okay? So in the interaction picture, my observables evolve according to U0. And what is U0? U0 is the time evolution operator that's generated by H0. Okay, so U0 is that. We know how to do that. What about the states? Well, the interaction picture state we take out the free evolution from the Schrodinger picture. Okay, so that's U dagger. Of course, what that is that, right? Because this is the full time evolution, and then we removed that amount. Okay? All right? So now what we want to see is, what is well, this thing is some, I'll call UI. We'll see that combination. We'll come back to that in a moment. Of course, this is also, everything agrees at time equals 0. So whatever the state is at time equals 0, in all pictures is the same. Whatever operators it is at time equals 0 is all the same. So what I want to see now is, what is the Schrodinger equation in the interaction picture? What is the differential time-dependent differential equation, which tells me how this state evolves as a function of time? So let's just do it. So, the time evolution of the state in the interaction picture is equal to the time derivative of U0 dagger acting on the Schrodinger picture state. Okay? Get myself a drink. So now we just use the product derivative rule. First, I take the derivative of this and act it on that. And then I take the derivative on the state itself in the Schrodinger picture. Okay? Now, this is generated by H0, right? So we have that written down there somewhere. It's on that board. We have to take the dagger of it. So the dagger of it gives us a plus I over H bar. And then we have to take the dagger which reverses the order. Right? So that's this. Right? Just looking at that. And then we have this guy, which is plus U dagger of t. And what is the time derivative of the Schrodinger picture state? Well, that's the full Hamiltonian, right? So this is minus I over H bar, full H of t acting on the Schrodinger picture state. I'm there, yeah, there it is. Okay? So now we can combine terms, right? So what do I have here? This is then equal to minus I over H bar, U0 dagger, H of t minus H0. Okay, that's combining these two terms and just writing them in the other order. Acting on the Schrodinger picture state. What is this? That's the interaction Hamiltonian. Okay? And now finally, let me insert, as I have the liberty to do, to introduce a U naught dagger here. That's the identity. That's cool. I can do that. So that gives me minus I over H bar, U naught dagger, H int of t, U naught, acting on U naught dagger of t on the Schrodinger state t. This is the interaction picture state. Okay? This is the interaction Hamiltonian in the interaction picture. Because if we come back to this board, what we said is observables in the interaction picture, we put the time evolution of the free into the observable. Okay, so let's come back over here. This is H int. And this long, complicated derivation gives us what we really want. What we have is that in the interaction picture. The state evolved according to a Schrödinger-like equation, a time-dependent Schrödinger equation, with a Hamiltonian that is given by the interaction Hamiltonian in the interaction picture. So that's the time-dependent Schrödinger equation that we know and kind of love in the interaction picture. Time-dependent Schrödinger equation in the interaction picture. Okay. Said another way, as we wrote it before, the solution to this is equal to the time evolution operator in the interaction picture acting on the state. Where the time evolution operator now is not the full time evolution operator, but it's a time evolution operator generated by the interaction Hamiltonian in the interaction picture. So to solve generally now for the solution to the time-dependent Schrödinger equation, we have to solve either this differential equation or find the solution for u and then just apply it. Now, again, we can't just integrate this simply, because generally this time-dependent operator does not commute with itself at different times. So we have to be careful. But we can, what we're interested in here is not the exact solution, because the exact solution to this is generally impossible. Not always. We can have certain special, and we'll look at some cases where we can solve this. So instead, we seek solutions to lowest order in the interaction. This is why it's perturbation theory, and not just the solution to the time-dependent Schrödinger equation. So the way we do that is we can write down a formal power series solution to the time evolution operator in the interaction picture. And that formal power series solution is known as the Dyson series. And what is the Dyson series? Well, let's write it down. So, I can just write this down, a formal solution here, which says that the time evolution operator prime t is equal to the boundary condition minus the integral of this from 0 to t dt prime h into dt prime u. Now that's not really a solution to anything, because I have u of t on u on both sides of the equation. This is just a formal integral, right? But now I can iterate. First of all, what is my time evolution operator at time equals 0? It's the identity. Okay, so that's our boundary condition. So now I can take the solution and plug it in again. Plug in for this, given the solution. So now I have this is equal to 1, the identity, minus I over h bar and then plug in for this. Well, that's 1 plus the integral 0 to t. And now I'll use a new dummy variable, dt double prime. Okay. I just plugged in the solution again as a formal solution. And I can go one more time, and then I'll quit. Right? This is plug in for that again. And that's 1 plus the integral. Oh, I guess I've got my minus I over h bar. Sorry. Minus I over h bar 0 to t triple prime. U of h t triple prime. U t triple prime. Etc. And what you see is I get a power series solution in multiple powers of the interaction Hamiltonian. Okay? All of these should be h int, pardon me, and all of these are in the interaction picture.
Shouldn't there be a plus after the first integral? Because if you do a power series, shouldn't you be adding together and multiplying them?
I'm sorry.
Because you have like the bracket of the next one right after like the first integral, you have times a bracket. Shouldn't that be a plus to bracket? Because if you
No, I'm plugging in for u, and what I plugged in was this whole solution again, and I plugged it in
okay,
there.
okay.
Yep, that's what I'm doing. Okay, so let's write the first few terms of that power series F. So, that means that the time evolution operator in the interaction picture is equal to the identity minus I over h bar 0 to t dt prime h in the interaction picture dt prime. So this, and then I have plus minus I over h bar squared integral 0 to t. Ooh, made a mistake here. This was u at t prime. So this is t prime. This was ut double prime. So that's t double prime. So this goes from t prime, and then an integral t double prime goes from 0 to t prime h t prime h t double prime plus and then the third order term, and then I'll quit. 0 to t prime, 0 to t prime, t double prime, 0 to t double prime, t triple prime, h t prime, h t double prime, h t triple prime, plus, and so on. That is the Dyson series.
Minus I over h bar cubed.
Cubed. And all of these, of course, are the interaction Hamiltonian. And I'll stop. This is all in the interaction picture. I don't want, there's just too many decorations on this thing. Okay? So just let you know in the interaction picture.
And H, no matter the primes, are all the same thing, right?
It's the same function.
So it basically just gets repetitive at this point. You know what H int is.
Yeah, indeed. It's already repetitive. Triple prime there. Okay? All right. So, now, there is a more compact way of writing this expression, which is the following. I claim that this expression is equal to what is called the time order product Now, this is the expression that we would have if the operator commuted with itself at different times. But I claim that it's not the solution generally, because generally this thing doesn't commute with itself at different times. Okay? This operator is known as the time ordering operator. And it's defined as follows. The time ordering applied to the product of two operators, A at T1 and B at T2, is equal to this if T1 is less than T2. And it's equal to this if T2 is earlier than T1. That's the definition. So this is the definition. So whatever string of operators you have, you order them in this way.
How does that apply to an exponential?
Right, so let's do that. So of course the exponential function, this is equal to the sum n equals 0 to infinity, 1 over n factorial, minus I over h bar to the power n, times the integral to the power n. No, to the power n. Okay? So now we're going to, in this we're going to have multiple products of Hamiltonians. You have to order every single one. All the string, what this time ordering operator will do is to order every term with all the earlier t's to the left of the later t's on the right. So the exponential, you do it in a power series. Let's look at the term, the first term is here. That's cool. That doesn't make a difference. There's nothing to order. But what about n equals 2? Let's just look at that term. So let us consider what we have over here. The integral from 0 to t dt prime, 0, oh, no, let's consider this. Okay, that's the second order term in this power series. Okay, so that is equal to right? Just writing it out. So that is an integral. If I think about the parameters, there's t prime and there's t double prime. And we're integrating from 0 to t here and 0 to t here. Okay. Let's compare that to what we actually have in the Dyson series. That's this guy, the second term. This integral, t prime goes from 0 to t, but t double prime only goes up to t prime. T double prime is always less than t prime because you integrate up to t prime and not beyond it. So you're integrating in this over this region, right? T prime goes from 0 to t. And t double prime goes up from 0 to whatever t prime is at that value. Okay? Of course, what this integral is just a sum of those two integrals. I could say this, I could break this integral into two integrals. An integral over this guy, this triangle, and then a second integral over that triangle. Okay? So this guy is an integral up on that first triangle. Right? And then an integral on that guy, t prime goes to 0 to t double prime. So now I'm just integrating t prime goes from 0 to t double prime goes from 0 to t, and t double prime goes from 0 to t prime along that guy. That's this integral. Okay? So these guys, now, if I switch these guys, if I can put this side on this side, then that's really, this integral is exactly the same as that integral. It's just a relabeling of t prime to double prime. So this is equal to twice the time-ordered product. Okay? So that is to say that this integral here is equal to a half the time-ordered product. You have to play around with it a little bit, but it's, from what I just showed you, it follows from that. And so forth. You have to permute this 3 different ways for the third case. It goes over 3 factorial. So it's the number of perturbations for each one.
Shouldn't this just be twice then?
No, this part of it is half of this guy,
Okay.
right? Because this whole thing is twice. So the bottom line here, we'll just quit here, is that the time evolution operator, and this is a form, if you ever get it in studying Feynman diagrams and quantum field theory, it's a very useful form. It's a formal kind of thing. We call it the time-ordered exponential. It means this, but it's a very complicated beast. We're never going to really use this here. I just wanted to introduce you to the full solution. Ultimately, what we're going to be interested in is perturbation theory, which means that we're only going to go, this is the lowest order, 0th order perturbation, 1st order perturbation, 2nd order perturbation. And we will continue that tomorrow night. All right? Have a good afternoon, everybody.